Yes, we can.
Okay, now I see also the presentation. First of all, thank you for this nice introduction. Thanks to the organizing committee and the program committee, and especially the organizing committee, because I'm really amazed what they were able to do in this very difficult period. So congratulations. Today we will talk about Spintronics, which means the possibility of transferring information with spin instead of charge of the electrons. And especially we will see what is the contribution of the quantum crystallography. But in order to arrive at showing what we can do, there will be some kind of long introduction on the development, basically, of the quantum crystallographic techniques over the years to arrive to the modern techniques that enable us to analyze materials. I will not show very many materials, but will be concentrated mainly on magnetic coordination networks. So I may disappoint those who were perhaps expecting inorganic materials here. We'll very, very briefly discuss about single molecule magnets, but it's a field that has been already touched earlier in this meeting, and then I will possibly draw some conclusions. Let's start with the charge and spin density of metal ions, and let's see a little bit of history. Well, everybody is aware of this word, the crystal field theory, which was introduced by Hans Bethe in the early 1930s or late of 1920s, actually. How do we arrive at the crystal field theory, and what does it mean, really? We all know that if we start with the electronic configuration of an atom, and we have an Hamiltonian, which is simply the summation of the one electron functions for that atom, this is just a rough indication of what is the energy of that atom, because more properly one has to take into account the perturbation, which is that of the repulsion between the electrons. And if we do that, then we see that actually we have different energies divided in terms, and the terms basically reflect the total angular momentum of that atom. And of course, we may have different summation of this total angular momentum given a particular electronic configuration. And moreover, there is a different possibility of having spin state, so that the so-called multiplicity 2s plus 1 may be different in different terms. But that's also not enough, because we may have a coupling between the spin and the orbit, and this gives rise to the so-called levels, where we have to add an additional number, which is J. And if we apply magnetic field, if we are under a magnetic field, we are also able to visualize the different energies of these so-called states. Okay, this is what happens in an atom, if you want, also in an ion, cation or anion. If we're dealing with transition metals, we are mainly dealing with cations. But we are ignoring at this moment what's the surrounding. So at this moment, our field is spherical. It's the field of the produced by the nucleus only of that atom. What Hans Bethe did was to consider the field around an atom, and he called it the crystal field, actually, because he was simulating the surroundings in terms of ligands by electronic charges, negative electronic charges, normally, if you consider that the metal is a metal cation, which induces, of course, a spatial distribution of the electrons, which is no longer spherically distributed, of course. It forces the stabilization of particular states. And actually, this can be seen as a kind of perturbation at the level of the terms. Okay, we have the terms, we can perturb them, and we create these states, which, according to the so-called Taname and Sugano diagram, they are proportional to the energy of these states is proportional to the extent of the crystal field perturbation. Now let's focus a little bit on the term crystal. Why was this called crystals? Actually, it's the only example, or one of the few examples, in which the effect of the crystal was probably exaggerated with respect to its actual role. In fact, as Brian Figgis, in his famous book on ligand field theory, now we'll come and see what is the ligand field instead, wrote was that beside all these considerations were driven by the X-ray studies mainly on salts in crystals, and therefore the perturbation was called the crystal field perturbation, and the theory was called the crystal field theory. Very few of these results actually depend on the fact that there is a lattice. As a matter of fact, a more appropriate name was the ligand field theory, later introduced by Van Vleck. But this was not just a change of the name. Actually, the name was very important to be changed because really it more properly represents what's going on, that only the first surrounding are determining these changes in the metals. The change was also substantial, however, because instead of considering just point charges around the atoms, now one consider orbitals. So the ligands are associated with the charge, but also with the possibility to have a delocalization of electrons with the transition metal. So in other words, now we are including the possibility to have covalency. And here is just one example with 2 electrons in the D shell of a transition metal. Here we have the so-called terms, which are basically the irreducible representation of the spherical point group symmetry of the atom. And then we have the terms that becomes states with particular names here, that depends instead on the irreducible representation of the particular point group, which is now established with by considering also the ligands. This also is followed by a number of phenomena. I will mention 2 of them, which are, one is very well known, the other one I'm not so sure. It will be a nice test to see if you remember that. So the first is the Young-Teller distortion. This is very well known. Young and Teller basically stated this theorem, which says that any nonlinear molecule or molecular ion having a degeneracy in the orbital is unstable and will distort in order to remove that degeneracy. Now here the example on a D9 system, so 9 electrons in the d orbitals, which are split in 2 groups according to the octahedral field. So with 9 electrons, we are basically considering copper 2+, for example, which is a metal that we will encounter very often in the rest of this talk. With 9 orbitals, with 9 electrons, of course, there is an unstable degeneracy here at the EG orbitals, so that a distortion from the octahedral down to a subgroup, in this case a tetragonal symmetry like the D4H, will basically adjust this problem by stabilizing one of the 2 orbitals against the other one, and of course having a double occupancy in this orbital and a single occupancy in the other one. Now these orbitals involved are those that point directly along the directions of the ligands. So X, Y, and Z are the 3 directions, and the ligands are distributed octahedrally around the atom in these 3 directions. If one of them is doubly occupied, then the best solution is a distortion, meaning an elongation of this direction, and therefore a lowering of the symmetry. The consequences are the creation of a so-called magnetic orbital. The dx square minus y square is now singly occupied. It's perpendicular to the Young-Teller distortion. So when we see distortion in one direction, we know that perpendicular to that direction, we will have a magnetic orbital, which is very important, of course, for the magnetic network under consideration. The other important effect is how large is this splitting. If there was no field, as we have seen, there will be no splitting. But if there is a splitting, then it means that the effect of the ligand is such that it creates a significant difference between these 2 sets of orbitals. And this field splitting can be proportional, therefore, to either the negative charge of the ligand or to the covalent power, or both, if you want, of the ligands. And this gives rise to the so-called spectrochemical series. The atoms and ligands on top of this rank are those that produce more covalent interaction with the metals. And those down are instead those that interact more weakly. Now, the second effect may be less well known, and this is the so-called nepheloxetic effect. Nepheloxetic means cloud expanding. We have seen before that there is repulsions between the electrons, and these repulsions eventually give rise to the terms and then to the states. But when we insert the metal into a complex, so into the field of the ligand, we observe a very important and strange phenomenon in a way, that the cloud of the metal expands. This is counterintuitive if you think about, because you put electrons in a field of negative charges, you should observe a contraction, and instead you see an expansion. Why you see that? Of course, because the ligands offer the metal the possibility to delocalize the electrons, and this is very important for all the phenomena, and especially for the magnetism. Now, this was measured by means of this. So the phenomenon was described by the Danish scientist Christian Jørgensen, but the effect is measured based on the parameters by Giulio Racca, an Italian scientist, who was parameterizing basically all the interactions that we have described so far with 3 parameters, A, B, and C. And B was in fact the repulsions between electrons. Now, the repulsion in the isolated ion is something. In the complex is smaller because there is this expansion. So the ratio beta between the complex and the free ion determines the rank again. But this time, those with the lowest rank are the better, of course, depending on what you want to do. But anyway, the ligands that mostly allow the metals to delocalize their electrons. That's very important. Okay, now, what we can do with crystallography then? We have seen already the lecture by Dilan Yayatilaka 2 days ago, saying that basically the quantum crystallography means that we deal with the wave function. Now, this is not such a recent objective. Read this sentence and try to guess who wrote it. The sentence is, I think that it is very interesting that one can see the psi function of Schrödinger's wave mechanics by means of the X-ray study on crystals. And this work should be continued experimentally, and I believe that more information regarding the nature of the chemical bond will result from it. Now, probably you recognize the nature of the chemical bond. So this is a statement by Linus Pauling in 1926, writing to the head of his department, basically asking money for setting up an X-ray laboratory. Okay, very elegant way to say that. And this means that at that time, it was already quite clear, and Pauling did nothing in reality so far, so everything was already done by Bragg, Compton, and Debye, that there was the possibility to determine or to get information about wave functions of ions, molecules, isolated atoms. Well, not really isolated if we deal with crystals, of course, for the reason I said before. But it took some while to get this realized, because only some 30 years later, it was possible to start getting information from X-ray diffraction on the electronic configuration of metals, here in pure metals. And this is the work by Dick Weiss and DeMarco, who studied a number of pure metals. Very difficult, actually. Still nowadays, it would be very difficult. And there was a project of the commission some years ago going on, and still going on in a way, to try to see what is the best method, including electron diffraction nowadays, to determine the precise electron distribution in metals. This work was exceptional, although it contained some mistakes, or at least some inaccuracies, especially due to the fact that there is extinction, and extinction of X-ray diffraction is a terrible problem that was not solved yet at that point. And therefore, some of these results, as Weiss admitted himself in his autobiography, were significantly biased. But anyway, he was the one who initiated the series of conferences called the Sagamore conferences on charge, spin, and later charge, spin, and momentum densities, starting from 1964. And it was clear from the very beginning, even from the announcement of the first, actually this is the report of the first meeting, that there was an interest for the determination of the wave function. And more clearly in his book, History Determination of Electron Distribution, although mainly dealing with the problem of determining electron density in position and momentum space, he was suggesting a method to calculate a corrected wave function, more or less doing the same kind of perturbation that we have seen before. The idea is you can start with a, oops, sorry, I was trying to get just a pointer. You can start from a given solution of the Schrödinger equation with the best Hamiltonian you can afford. So you will get a wave function. And this wave function is, of course, not fully correct, because it will not take into account properly perhaps the electron correlation and many other effects if you want. But so you can also apply a kind of perturbation theory, but you're perturbing Hamiltonian H prime, instead of being a physically known Hamiltonian, it could be written as the error Hamiltonian, so a function of the difference between the observed X-ray diffraction, so the one that you can measure, and those that you can calculate. He was, of course, referring only to Hartree-Fock method, because at that time this was already the maximum that you can get. This was not so immediate, however, to be put into practice, and actually never really put into practice in this way, because years later, and you have seen already in the lecture of Dylan, Dylan Yayatilata came out with this idea, which is somewhat similar, but not exactly in the perturbative scheme. This is more a restrained regression. The initial Hamiltonian is used to produce a new functional, taking into account also a chi distribution of the difference between the observed and calculated X-ray factors, and can be used to calculate a new wave function, which is, if you want, an X-ray wave function. Now, I don't want to enter into the discussion that was already done about the measurement of the wave function. Some people may certainly complain that this is not strictly possible, but Tiran has already explained what is the meaning of doing this. An alternative is the refinement instead of elements of the density matrix, or a calculation with some kind of constraint to the X-ray diffraction intensities, again, of the density matrix. Anyway, two techniques. The first one is now very popular, has become very popular. The other ones are still in a niche, but they are the way to basically respond to the idea of Weiss. And there are many other techniques that have been proposed in the past. I want to especially focus on, for example, on the valence orbital model by Figgis and Reynolds. This was a kind of way to translate really the ideas, the concept of the valence of the ligand field theory into the diffraction modeling. Then others like the X-ray atomic orbital, later called X-ray molecular orbital, and the spin resolve atomic orbital model that was presented 2 days ago by Nicolas Clésier, for example. They are all ways to localize somehow your problem only on the metal atom, perhaps, in order to describe and to calculate coefficients of the part of the wave function. I mean, the one which is interesting for us, for example, the one that describes the d orbital. A different approach is this moon instead, because here a molecular orbital wave function is calculated, and then occupation numbers of these molecular orbitals, including the virtual orbitals, are refined against X-ray. So this is completely different kind of approach, whereas the others are somewhat similar. I'm not saying that they are the same, but they have a similar concept. Well, the history, however, is that the alternative was to define directly a model of the electron density, and this was the work mainly done by Bob Stewart and Phil Coppens, although a significant contribution came from Fred Hirschfeld and Kurt Sonio as well, who basically said, well, let's forget about the wave function, let's refine the electron density, which is somewhat easier, especially because you can construct a model which is not that different conceptually from the model that you normally use for the determination of the crystal structure. So the electron density in a unit cell is expanded in terms of atomic electron density. This is exactly what you have in a normal structural refinement, but then each atomic electron density is further expanded in shells, so core, valence, and if you want, you can define different level of valence, and then with a population, which means the atom may be non-neutral, they may be charged, positively or negatively charged, and there is a deformation also that takes advantage of spherical harmonics. So these functions here are the spherical harmonics, the same that you use for orbitals, but here used for density function. And of course, as we have seen before, there's a proportion between the two. One is the square, basically, of the other. Important, we're talking about the neophylacetic effect. Well, this kappa parameter here is used to scale, basically, the radial distribution of the electron density, allowing an expansion or a contraction. Basically, with a kappa larger than 1, you have a contraction, whereas with a kappa smaller than 1, you have an expansion of your cloud. And if you do normally transition metal complexes, you always find out that this kappa is smaller than 1, so there is an expansion, even though the electronic configuration you start from is perhaps the neutral atom configuration. And this is even more counterintuitive, because if you have a neutral atom and you go into a ionic state, positive ionic state, then your shell should contract, not expand. But it actually expands. And this expansion is, of course, the manifestation of the neophylacetic effect in the X-ray diffraction language. Here, let me also remind here a person who just left us with Tibor Korytansky. He didn't develop these models, but he was the one who put into suitable codes like the XD codes that was mentioned before by Christoph. Tibor had an accident, unfortunately, a couple of months ago, and he died. But what is important is that from these densities, you can derive orbital coefficients for the transition metal, for example, under a special assumption. So normally you wouldn't be able, because if your electron density comes from the combination of many atomic orbitals into molecular orbitals, and then this is the density is the square of this, it's very difficult to retrieve the atomic coefficients, of course. But if we are in a situation like the one depicted before, with a relatively low overlap between the ligands and the transition metal, the center metal, then it is possible to do this operation, because you can calculate all the possible products of these orbitals. So there are 5, of course. They would produce 25 orbital products, but the cross products are symmetric. So 10 of them are just the replica of other 10. So there are only 15 of such products. And we can use a particular property of the spherical harmonics. They represent a closed group, which means that the product of 2 such spherical harmonics is exactly a linear combination of other spherical harmonics. And in particular, these spherical harmonics of the d orbital are like quadruples, so with L equal 2, and their product would produce hexadecapoles, quadruples, and monopoles. And if you count the number of monopoles, so 1 monopole, the 5 quadruples, and the 9 hexadecapoles, you end up with 15. So you have exactly all the terms that you need in order to construct a system of equation, and therefore with a spatial matrix, first devised by Ed Stevens, you can retrieve from the multipolar coefficients the orbital coefficients. Now, this is very useful, but there is another point to consider, that here we are not applying any constraint to the Pauli principle. So it could be that this population exceeds the 2 electrons per orbital that you would expect to obtain from the Pauli exclusion principle. Another important point is that for the multipolar model, you can decide either to have a global coordinate system, so the same of the crystal, like you do for the atomic displacement parameters, or you may have a local coordinate system. In this case, you define locally what are your axes X, Y, and Z. And thanks to this work by Coppens and Sabino, it was possible to find the best local coordinate system for each transition metal by assuming that the best one is the one that minimizes the cross products, so that your density population matrix is closer to a diagonal matrix. It would be a diagonal matrix if there is no perturbation at all and the atom is in isolation. But it is not if there is the perturbation. But if you minimize it, then you have probably found the best z-axis, which is, of course, the quantization axis. Very important, and we will see one application done in coordination networks. Then, with this model, it is also possible to split the population terms depending on the spin, so alpha and beta, either for, oops, I went one too far, either for the valence or the deformation part of the valence. You can have this double occupation, but you need to have not only X-ray diffraction in this case, but also polarized neutron diffraction. And in this seminal work by the French group of Leconte, Brecker, Maxime Deutsch, and Mohamed Sossou, and Jean-Michel Gillet and Nicolas, they have in fact used also the unpolarized neutron diffraction in order to refine all possible coefficients. You see that there is at least one source of information that gives you each of these parameters. Apart from this, of course, there is the spin resolve X-ray atomic model that was described by Nicolas on Sunday. Okay, now let's come to the last point of this quite long introduction, I have to say, about how the atoms do exchange the information. They know, of course, we know, of course, that the coupling between magnetic moments on atoms could be ferro or antiferromagnetic. If the moments are localized on the same, the spin moments are localized on the same atom, then the coupling is, of course, very large, but there is little information which is propagated in this case. So we need to have coupling between different atoms. The coupling between different atoms can be explained by this J coupling here, which is simply a function of the difference in energy between the antiferromagnetic and the ferromagnetic states. Then it is scaled for the spin state of the system. If this is 1 alpha as in the classical copper 2 plus networks, then this is just overall a plus 2 terms. J positive means that the coupling is ferromagnetic, and negative that it is antiferromagnetic. But there are different effects, like the Coulomb effect and the direct exchange between the atoms, that favor the ferromagnetic coupling, whereas the Opping, which is a kinetic term, basically kinetic energy term, it favors the antiferromagnetic coupling, so that eventually the interplay between these give rise to the final sign of the coupling constant. One can use Hamiltonians of this kind, where the coupling constant between each spin center in the lattice is used against, for example, data that comes from superconducting quantum interference, mainly known as QUID, or from muon spectroscopy, or from tunnel diode oscillators. And this is roughly an idea of how the coupling constants behave. So you see that the direct exchange favors the ferromagnetic, so the positive value of J, as well as U, because U is here denominator for T. T is the opping, which goes with the square, but with a negative sign, so it will favor instead the antiferromagnetic kind of exchange. We can see different kind of mechanism for the exchange. One is the spin polarization, where each metal center tend to polarize a particular spin, and therefore, if there is an atom in the middle acting, or a group acting as a non-magnetic linker between the two atoms for the so-called super exchange, then we will have this kind of spin distribution. Whereas if there is delocalization, then we have this kind of coupling. It doesn't mean that spin polarization or spin delocalization always favor this kind of eventual coupling, because it depends very much on how many atoms and how they are distributed in the interconnections between the metal centers. So this is just two general kind of schemes. Then we have the Goodenough and Kanamori rules that I will only very briefly show here, because these are arguments of one of the talk in the next micro symposium session. If we have an alpha field transition metal orbital in one metal center, and then we have a non-magnetic linker here, then this is the classical kind of coupling that you would expect for an 180 degrees orientation, whereas this ferromagnetic coupling is favored when you have a 90 degrees orientation. Are quite empirical rule, but they are extremely efficient. We will see, or you will see in one of the micro symposia, there is a talk about this. And last but not least, how we do calculate this from first principle? Well, as I said, we can calculate, of course, the difference in the states, but in a normal crystal, there are many possible interactions, and one wants to visualize each and every interaction. And so either you calculate several kind of spin states in your crystal, and then by making all these kind of difference, you are able to show, for example, what is the kind of coupling between these two atoms. You have to calculate this spin distribution and this one, of course, and then you will see if these two are ferromagnetic or antiferromagnetically coupled, leaving the rest untouched. And the same you can do for other kind of interaction. Very important, however, if the J coupling depends also on the direct exchange, then you can't use a simple DFT. You must necessarily use a DFT that contains the Hartree-Fock exchange. Otherwise, this term is lost and your coupling constants go crazy. There is an alternative, which is that of doing calculations instead of taking the crystal. You take a fragment of the crystal, the one that is of interest for you. You do, in this case, a molecular kind of calculation, which could be more accurate, however, from the point of view of the calculation. And you can see, for example, the spin density distribution, and again, calculate the coupling scheme. We will see an example also of this kind. Because we are dealing with an exchange, there is an important parameter that we will see is very relevant. That is the so-called delocalization index, as introduced in the theory, the quantum theory of atoms and molecules by Bader. And this delocalization index is basically telling us how much exchange is there between two atoms if atoms are defined with the classical partitioning of the quantum theory of atoms in molecule. And this is basically coming from the double integration of this, in these two atomic basins, A and B, of the so-called exchange correlation density. And this gives rise to this delocalization index called also delta. Okay, some examples. I don't have enough, very much time, of course, to show many examples, but let's see a few of them anyway. We have seen all the theoretical background. First of all, we deal with antiferromagnetic spintronics. There's this interesting statement by Niels in 1970 at the occasion of his Nobel lecture. He said that antiferromagnets basically explain us how antiferromagnets work. Are extremely interesting, of course, but they have no application. Actually, this came out to be a very, very wrong statement, because nowadays most of the application in spintronics depends on the coupling between ferromagnetic and antiferromagnetic materials, and the role of antiferromagnetic materials is essential. So we are dealing and we are searching for efficient antiferromagnetic spintronics materials. One of the first examples of coordination networks investigated with charge density approach was this manganese formiate network, hydrated actually. So the manganese is surrounded by formiates and by water molecules. It was studied by Jacob Overgaard and Bo Iversen, and I think this was also one of the first coordination networks in general, but especially the first coordination network, which is magnetic. They, of course, investigated the distribution of d electrons in the two symmetry-independent manganese atoms in the structure. And because this was a monoclinic structure, so, and as you can see, the layer is quite distorted, it's not very orthogonal, then they applied the Coppens and Sabino reorientation of the local coordinate system in order to find the best direction of the z-axis, which is in this case is not so straightforwardly determined. As you can see, when you do this kind of operation, the total population of the D shell doesn't change because you are just rotating the coordinate system. But of course, the occupation in the individual orbitals does change. And this is important with some important implications. I now switch to some examples we did instead in my group with Leonardo dos Santos. Here we are dealing with copper, pyridine nitrates, or copper pyridine nitrate and hydrate. In the second case, we have two pyridine per each copper atom, and this forms a quasi two-dimensional kind of network where the nitrate is Jahn-Teller distorted, and so the magnetic exchange should go through the pyridine, but we will see also that this is in fact the case. Or we have quasi one-dimensional network in the other case, because here we have two nitrate ligands, and one is also coordinated to the metal, not in the Jahn-Teller distorted direction. Of course, we calculate the orbital population, but the most important thing is how to calculate the various exchange possibilities in the two structure. And you see that we figure it out 5 possible paths for each copper-copper interaction, but only one of them in both cases is the dominant one. And this is the one going through the pyridine ligands with a coupling constant, which is of course antiferromagnetic, but very weak or surprisingly weak. Anyway, perfectly in keeping with experimental observation, so obtained from conducting quantum interference. Very similar is the approach molecular, dividing so the 5 possible terms, or the approach crystalline, so obtaining the final coupling in the periodic DFT calculations. But the difference, of course, is that in one case you have 2 such exchange paths, and therefore the system is bidimensional. Important, why is the pyridine not so good as exchanger? One would expect that an aromatic system, thanks to the pi system, would allow a good exchange, but actually this is not the case. Instead, in fact, the mechanism is going through the sigma channel, which has not particularly large exchange between atoms, and therefore the overall exchange produced through the pyridine is not particularly large. The reason is that this pi system is always perpendicular to the magnetic orbital, so it's unable to carry any kind of spin interaction. This was proved also by analyzing the profiles of the ellipticities of the copper-nitrogen bonds, for example. And it is quite clear also from the spin density distribution, where you see that there is no pi interaction. At the same time, there is a strong nepheloacetic effect. Now, again, with the copper pyrazine, we investigated this system in which there is pyrazine, fluoride, and water coordinated to the copper metal. Well, when we see this structure, with just a 1-to-1 ratio between the copper and the pyrazine, you would immediately expect to have a one-dimensional quantum magnets. But actually, this structure is very peculiar because the Young-Teller distortion here goes through the copper-pyrazine system. That's surprising because the copper-nitrogen bond, actually, because why is so surprising? Well, if we go and see the spectrochemical series, we see that the aromatic amine are definitely bigger than water and than fluoride. Moreover, the nepheloacetic effect, but remember this has the opposite kind of ranking. Again, the aromatic amine has the smaller beta, which means the largest possible delocalization. Therefore, everything everything would drive us to think that there is no distortion along the copper-pyrazine bond. Instead, it should be along the copper fluoride. This is in fact an exception. If you search in the entire Cambridge structural database, you find only two compounds with this peculiarity. One is this one, and the other one is another one that we studied, in which we have two copper atoms per pyrazine, because we form a little cluster of copper. Now, we decided to put this under pressure. We decided to put this system under pressure. And first of all, because the pyrazine is Young-Teller distorted, then the magnetic network is not going through the copper pyrazine. It's actually going through the hydrogen fluoride interaction between water and fluoride, hydrogen bond interaction, sorry, between water and fluoride. And so it's forming a two-dimensional network, weak, but the same kind of coupling as you see in the copper pyrazine system. But when you compress it, what happens is that at 1 GPa, there is a change of the Young-Teller distortion. Instead of being directed toward the pyrazine, now it's directed toward the water molecules. And then if you apply even further pressure at 3 GPa, now finally you reach what you would have expected from the beginning, so to have copper fluoride elongated because of the Young-Teller distortion. So you change completely the magnetic network, because after the first phase transition, it becomes a one-dimensional network, because now the copper pyrazine is the only propagation. And it is perpendicular to the network that is instead stable at ambient condition. There are other phases that can be produced at the same pressure. And in both cases, instead, the Young-Teller distortion remains along the water molecules. You can confirm everything with the spin density distribution. So you see in the alpha phase, then you see the beta phase, you have changed the magnetic orbital, and then finally this gamma phase. Or alternative, this epsilon phase, which retain the same configuration as the beta phase. A similar system, copper pyrazine, but this time in a tetragonal kind of system with a tetragonal network, is this one, copper an halide and then two pyrazines. Now the pyrazines form this blue layer, which is the square network. This time the Young-Teller distortion is perpendicular, so along the halide, or similarly you can find many other linkers that goes perpendicular, so you can have hydrogen fluoride, nitrate, and so on. This is a picture taken from the top, so you see clearly the tetragonal system. This is relatively simple, but when you apply compression, what you observe is, of course, a compression along the softest bond, and the softest bond is the Young-Teller distorted direction, actually. And this, at a given pressure, at about 10 gigapascal, you reach basically the same copper bromine or copper chlorine distances that you would expect when they are non-Jahn-Teller distorted. The coupling, which is initially very small along the halide, becomes much larger and even dominant. And this is correlated quite clearly with the delocalization index. You see here the delocalization index is growing as a function of pressure, reaching this particular combination of states that you obtain at 15 gigapascal, where you have either the delocalization through the pyrazine or through one pyrazine and the vertical halide. I have very little time to show instead another example, which is that of using copper formiate. Here with formiate, the situation is very different. The coupling is extremely large. It's 70 Kelvin. Kelvin is the unit of energy, unit used for the energies, of course, not the temperature. This system is peculiar because we have copper surrounded only by formiates. Then the dimethylammonium is inserted here in the cavity, in the central cavity. And in this system, therefore, the Jahn-Teller distortion is against one of the possible copper formiate distances. And along that direction, the coupling is still possible, but it is extremely weak. Situation changes, however, again with pressure. This will be, by the way, the talk by Rebecca Scatena in the next micro symposium, so I'm not entering too much into the details, but she will probably not discuss about what happens with the pressure. If you apply pressure, you change again and you reorder again your orbitals. And so you obtain a different phase in which you have shifted the direction of the Jahn-Teller distortion, and again changing the kind of magnetic network. I just prepared a couple of slides, but will be very fast about single molecule magnets. This mainly because Jakob Overgaard has already discussed on Sunday and presented some very nice examples. Just to say that sometimes we are, sorry, I go back because here there is an interesting sentence. Sometimes we use crystals because, not only because they are enable us to see the electron density, but also because they are basically the incubators where we produce our materials. But sometimes we use them because they are the lenses that enable us to see the molecules much better. It's in a way very compatible with a statement by the president of the IUCr in the IUCr newsletter early this year. He was distinguishing between the crystallography science and crystallography technique. But sometimes this crystallography technique is extremely important. It's normally adopted for determining molecular structure, but sometimes also for determining magnetic structure of single molecule magnets. I'm not going farther, but just to say that he explained very nicely how the magnetic anisotropy can be determined from X-ray diffraction and charge density. Now, the outlook is very simple. We have shown how the history of crystallography is linked with the magnetism. And here we have given a perspective which is mainly from the chemical point of view with coordination networks. The quantum information technology depends very much on explaining phenomena like the magnetic superexchange and the stabilization or destabilization of particular magnetic states. Here is where quantum crystallography can provide some information. What we may expect to have in the future, because these hybrid organic and inorganic materials are growing, it is very important to obtain more and more information about this exchange, which is not fully understood yet, and especially not fully understood for all possible linkers. So there is a lot of work that could be done. And let me also comment on the fact that so far, most of the measurement that we do in quantum crystallography are classical measurements in reality. We are not doing quantum mechanical measurement, but it would be very important, especially if we want to really face the problems of quantum information technology. And I just want to acknowledge the collaborators who enable me to present these results. They've been shown also as pictures during the slides, so I don't have to name them again. and I wish to thank you for the attention.
Thank you very much, Piero, for this crystal clear, truly magnetic lecture. We have time for 1-2 quick questions as the break already started. Are there any questions in the room? I can see a question from Joanna Savago from Cambridge Crystallographic Data Center. Piero, how would we go about designing ferromagnetic and antiferromagnetic materials? Do we understand what make them in one way or another? Do we need the experimental wave function to assess them? What would you answer to Joanna?
So, of course, if you can quantify more substantially those rules by Goodenough and Kinamori, then probably we will have the instrument to design materials, because this means that for each and every kind of linker, you will know how they provide information on the magnetic exchange, and therefore this is very useful. Do we need always to get an experimental wave function? If you want to determine how this exchange works, of course, you must get information about the spin coupling and the spin states. So whether there is a ferromagnetic, antiferromagnetic, and how large is this coupling. The rest of the wave function may not be fully necessary. Okay, so but certainly one part is essential.
Thank you very much. Are there any more comments or questions? As I do not see any, and we cannot consume the whole break, let me finish this lecture. Let us thank Piero again for this fantastic lecture.
Thank you, and I really wished I could have been there, but unfortunately I couldn't come. And thanks to all the audience and to all colleagues, and see you soon, hopefully.
Thank you, Piero. The session is closed.